Imagine standing on the surface of Mars, no spacesuit, just you and the planet. In the first 10 seconds, 3 things happen at once. Because the atmospheric pressure is almost non-existent, the moisture in your eyes, mouth, and lungs begins to boil, not from heat, but from the lack of pressure. Your blood starts forming bubbles beneath your skin. At the same time, the temperature, averaging around -60 degrees Celsius, begins freezing what remains. You would lose consciousness in roughly 15 seconds. In under a minute, you would be dead. And this is the world we're seriously considering as humanity's next home. We often speak about Mars as the next frontier, a backup plan for civilization. Billionaires compete to build rockets. Space agencies outline mission schedules. Popular imagination has already designed Martian habitats with greenhouses and panoramic sunrise views. But beneath that optimism lies a harder truth. Mars isn't just difficult, it is fundamentally and relentlessly hostile to human life. And the deeper you examine it, the more severe the challenges become. Start with distance. On average, Mars sits about 225 million kilometers from Earth. At its closest approach, that shrinks to roughly 55 million kilometers. At its farthest, it stretches beyond 400 million. Even at the minimum distance, traveling non-stop at 100 kilometers per hour, the journey would take around 60 years. But distance isn't the true obstacle. The real problem is what awaits on arrival. First, the atmosphere, or rather, the near absence of one. Technically, Mars has an atmosphere, but it's less than 1% as dense as Earth's. Earth's sea level pressure averages about 1,013 millibars. On Mars, it's around 6. That's not thin air. By human standards, it's almost a vacuum. Your lungs wouldn't merely struggle, they would be physically incapable of extracting oxygen. And even if they could, there's almost none available. The Martian atmosphere is roughly 95% carbon dioxide. Oxygen accounts for about 0.13% compared to Earth's 21%. On Mars, you don't breathe. You suffocate while your body depressurizes. That thin atmosphere also means something else. Almost no radiation protection. On Earth, we're shielded by both a thick atmosphere and a global magnetic field. Mars lost its magnetic field billions of years ago as its core cooled. Without that protective dynamo, solar wind gradually stripped much of its atmosphere away. What remains offers minimal shielding. The Martian surface is constantly bombarded by galactic cosmic rays and solar particle events. Radiation exposure there is estimated to be roughly 40 to 50 times higher than on Earth's surface. Over a 2 to 3 year mission, the minimum for a round trip, astronauts would likely exceed NASA's current career radiation limits. The risks include increased cancer probability, potential cognitive impairment, nervous system damage, and accelerated cardiovascular aging. And shielding isn't a simple solution. High-energy cosmic rays can penetrate most conventional materials. When they strike metal walls, they generate secondary radiation, additional particles that can sometimes cause even more damage than the originals. Adding thickness doesn't automatically make habitat safer. In some cases, it makes things worse. Even if you find shelter inside a pressurized habitat, the danger doesn't disappear. The ground itself presents another threat. Martian soil, or regolith, contains significant levels of perchlorates, toxic compounds harmful to human biology. These chemicals disrupt thyroid function and interfere with hormones that regulate metabolism and growth. Any attempt to grow food would require extensive processing to remove these toxins, and the dust, impossibly fine and electrostatically charged, infiltrates everything. Mars regularly experiences massive dust storms. In 2018, a global storm enveloped the entire planet for nearly 2 months, cutting off sunlight and ending the mission of NASA's Opportunity rover. The particles are smaller than human red blood cells and cling to surfaces, damaging equipment, degrading seals, and covering solar panels. If your colony depends on solar power, a major storm could reduce energy production by more than 90%. And Mars experiences regional dust storms every year, with global ones occurring every few Martian years. Imagine relying on fragile life support systems while the weather can suddenly and drastically limit your power supply, and you're tens of millions of kilometers from help. These dangers don't exist independently. They compound each other. A dust storm reduces solar output. Reduced power forces rationing. Life support systems, air filtration, water recycling, heating depend on energy. If power drops too far, carbon dioxide builds up, temperatures fall, and survival becomes uncertain. Meanwhile, communication with Earth carries a delay of 4 to 24 minutes each way. There is no immediate rescue, no rapid evacuation, no abort option. On the International Space Station, astronauts orbit about 400 kilometers above Earth. If an emergency occurs, they can return within hours. On Mars, a return window opens only every couple of years. And that assumes your return vehicle still functions and your body can endure the trip. The human body itself presents another challenge. The journey to Mars takes 6 to 9 months in microgravity. During that time, astronauts lose 1 to 3% of bone mass per month. Muscles weaken. The heart shrinks slightly because it no longer pumps against full gravity. Blood volume decreases. The immune system becomes compromised. Fluid shifts toward the head, affecting vision. After 6 months aboard the ISS, many astronauts struggle to stand unassisted upon return. A Mars mission would last far longer. Mars's gravity is only 38% of Earth's, likely insufficient to fully prevent further deterioration. After spending years in reduced gravity and then months returning in weightlessness, astronauts could arrive back on Earth with severely weakened bones and muscles. Fractures could occur from ordinary movement. Cardiovascular strain would be significant. Some researchers suggest full recovery might never occur. And then there is psychology. Studies of isolated and confined environments, from Antarctic stations to submarine deployments, show measurable mental strain over time: depression, anxiety, cognitive decline, interpersonal conflict. Those environments, however, always include a safety net. Evacuation is possible. Earth feels reachable. On Mars, there is no immediate escape. The next launch opportunity home is years away. Communication delays prevent real-time conversations. Messages become delayed exchanges across millions of kilometers. Experiments like Mars 500 demonstrated psychological stress even in simulations where participants knew they could leave. Remove that knowledge entirely, and the psychological burden intensifies. So consider the full picture. Mars has no breathable air. Its atmospheric pressure would cause bodily fluids to boil. The average temperature is -60 degrees Celsius, dropping far lower at the poles. The soil contains toxic compounds. Dust storms can last for months and cripple power systems. There is no magnetic shield. Radiation levels are dangerously high. The journey there and back severely weakens the human body. Long-term isolation poses serious psychological risks. This is the planet we are preparing to send humans to. None of this makes Mars exploration pointless. Robotic missions have achieved remarkable success. Rovers and orbiters have revealed insights into Martian geology, climate history, and the possibility of ancient microbial life. We can continue exploring and learning without placing human biology in a scenario where every system operates at its limits. The argument often made is that humanity needs a second planet, a safeguard against extinction-level events. The logic is understandable. But is Mars truly a viable backup? A world where you cannot breathe without machinery, cannot grow food without chemical processing, cannot step outside unprotected, cannot shield yourself effectively from radiation, and cannot maintain long-term physical health without degradation. That is not a second Earth. It is a perpetual survival scenario. Some propose terraforming, gradually transforming Mars into something more Earth-like. But the timescales stretch across centuries or millennia, and the feasibility remains uncertain. There likely isn't enough accessible carbon dioxide to meaningfully thicken the atmosphere, and without a magnetic field, solar wind would continue stripping it away. At its core, the issue is biological. We evolved for Earth. Every cell, every organ, every chemical process in our bodies is adapted to this planet's gravity, atmosphere, and magnetic protection. We are not universal organisms. We are Earth organisms. Our fascination with Mars speaks to something deeply human: curiosity, ambition, refusal to accept limits. These traits have driven extraordinary achievements. But wisdom also lies in recognizing when physical reality imposes boundaries that cannot simply be engineered away. Mars is not an empty frontier waiting patiently for settlement. It is an unforgiving environment governed by physics that do not favor us. Perhaps the boldest path forward is not abandoning exploration, but refining it. Sending our machines, our instruments, our probes, expanding knowledge while keeping our fragile, Earth-adapted bodies on the only world we know, where we can walk outside without protection, breathe deeply, feel rain, and watch Mars shine in the night sky, safely from tens of millions of kilometers away.